In this video, we'll talk about the second derivative test, which gives us another way to analyze whether a critical point is a local max or local min using the second derivative. What's the sort of idea of this test? Well, the test here is you want to use the second derivative, not the change in the first derivative, to figure out whether something is a local max or a local min. Well, if I look at a graph that's concave down, our standard example is, say, negative x squared, well, it looks like the critical point here clearly has to be a maximum because this graph is concave down. Similarly, for a concave up graph, it looks like it's going to have to be a minimum. Well, that was just sort of intuition. Can we say anything more particular about how this works? So what did our first derivative test say? Well, for the first derivative test, we saw that f prime going from positive to negative across the critical point meant that we had a maximum. Well, what does this mean? Well, if my derivative is positive on the left and negative on the right, that means my derivative is decreasing through this point, right? This means my derivative here is decreasing because it goes from positive through 0 at the critical point to negative, which therefore means that f double prime is negative. And that's the idea here, although sort of in reverse. If f double prime is negative, that forces f prime to be decreasing, which means the only way it can go through 0 is by going from positive to negative, which means it has a maximum. And the same works the other way for a minimum, saying that if f double prime is positive, then the only way for f prime to go through 0 is by going from negative to positive because f prime is increasing, which means I have a minimum at this point. Now we put this together in an actual test. So let's say we have a function f. We're going to assume that our second derivative is continuous, just to make sure everything works out. And then we're going to let c be a critical point of f with f prime of c equals 0. If f prime doesn't exist, then f double prime also doesn't exist at that point, and therefore this test won't work. What are our cases here? Well, if f double prime is negative, that means we're concave down, then f attains a local maximum at c. If f double prime is positive, that means we're concave up, and so f will attain a local minimum at c. And the last case here is if f double prime of c equals 0. This is a weird case here because in this case, the test fails. And by this, I don't mean that there's not a local max or local min. I mean that this test cannot tell you if it's a local max, a local min, or neither. It just does give you no information about what's actually going on here. In this case, you would have to go back to the first derivative test to actually figure out if it's a max, min, or neither, because that test never fails. It's more complicated to check both sides of the point, but it doesn't actually fail. This test here has an inconclusive case here in case 3, where it does not give you an answer to what's actually happening at this point. All right, so this is an example of how you might use this test to analyze critical points. So I want to analyze all critical points of the function f of x equals x squared minus 8x over x plus 1. And so we first want to find all critical points, and then use this second derivative test to figure out what they are, if they're maxes or mins, or how they all work. So we want to start by taking derivatives here. So we find these by the quotient rule. We can then simplify out. And then we go on to take the second derivative. Again, by the quotient rule. We can again simplify out. I can first cancel x plus 1 from every term. And a lot of things here cancel, leaving me with an 18 over x plus 1 cubed. You could simplify f prime in a different way to get that a lot quicker, but you can work it out directly as well. So where are my critical points? I'm looking here at f prime, which was x squared plus 2x minus 8 over x plus 1 squared. This does not exist at minus 1. And at 0 over the top is 0. And since the top factors, x plus 4, x minus 2, this has zeros at minus 4 and 2. So at minus 1, I don't really have a critical point because the function also is not defined at minus 1. F not defined, so not a critical point. The two we have to worry about is minus 4 and 2. With our second derivative there, we can then figure out, based on the second derivative test, if these are local max or local mins. So at x equals -4, we know that f double prime of x is 18 over -4 plus 1 cubed. That's going to be a positive over a negative on the bottom. That number is going to be negative. Hence, this point is a local maximum. For the other point at 2, we get f double prime at 2 is 18 over 2 plus 1 cubed. That's going to be a positive number, positive over positive. Therefore, f of 2 is a local minimum. So second derivative tests can be simpler for figuring out things with local max, local mins. You can just plug into one function, namely the second derivative, and see what's going on. But it's the issue of sometimes it fails and doesn't tell you the answer. You have to go back to the first derivative anyway to actually figure out if that's a local max, local min. That's the idea of the second derivative test and how it works for classifying critical points into local max or local min.